Everyone, I'm Ridham. Today I'll be presenting on the 8-point algorithm, how we compute the fundamental matrix from point correspondences. I'll walk through the math, show why each step is needed, and then demo it on both synthetic and real images. So here's the setup. You take two photos of the same scene from different camera positions. The same 3D points show up at different pixel locations in each image. Using SIFT, we can find matching pairs across two images. The question is, without knowing anything about the cameras, no calibration, can we figure out the geometric relationship between these two views? Specifically, if we know where a point is in image 1, where must it appear in image 2? The answer is the fundamental matrix F. Given a point x in image 1, F gives us a line in image 2, the epipolar line. The true matching point must lie on that line. Computing F from 8 or more point pairs with no calibration needed is the 8-point algorithm. And once you have F, it unlocks all these applications: stereo depth estimation, 3D reconstruction, visual odometry, and structure from motion. So what exactly is F? It's a 3x3 matrix with rank 2 and 7 degrees of freedom. Its job is simple. It takes a point x in image 1 and maps it to an epipolar line L prime in image 2. That's this equation. L prime equals F times x. The key constraint is that any true matching point x prime in image 2 must lie on that line. Mathematically, x prime transpose F times x is equal to 0. This is the epipolar constraint. Why is this useful? Because instead of searching the entire image for a match, millions of pixels, you only search along one line. A 2D search becomes a 1D search. So let's expand the epipolar constraint. We write our points in a homogeneous coordinates. X is u, v, and 1, and x prime is u prime, v prime, 1. When you multiply out, x prime transpose f x is equal to 0. You get this long equation. The key insight here is that the coordinates u, v, u prime, v prime are all known. They come from our SIFT matches. The 9 entries of f are what we don't know. And crucially, this equation is linear in the unknowns. That means we can solve it with straightforward linear algebra. No iterative optimizations are needed. Each point pair gives us one such equation. So F is a 3x3 matrix. That means there are 9 entries, but it's defined up to scale. Since F works, any scalar multiple of a F also satisfies x prime transpose k. Fx equals k times 0 equals 0. That removes 1 degree of freedom, and the rank 2 constraint removes another. So F has 7 actual degrees of freedom. Technically, 7 pairs would be suffice, but the 7-point algorithm requires a cubic equation and up to 3 solutions. The 8-point algorithm uses 8 or more correspondences, and the system becomes fully linear. One SVD, one solution, and no ambiguity. It's simpler to implement and works well when combined with RANSAC. So here's how we set it up. Each point correspondence gives us one row in a matrix A. The row is just the products of the known coordinates in a specific order: u prime u, u prime v, u prime, v prime u, v prime v, v prime, u, v, and 1. We stack the 9 entries of f into a single vector f. Then the epipolar constraint for each pair becomes a dot product. This row times f equals 0. With 9 pairs, we get 9 by n by 9 matrix A, and our goal is to find f such that AF equals 0. With noise in real data, no exact solution exists, so we want the f that minimizes the norm of AF. That's exactly what SVD gives us. So we decompose A using singular value decomposition. A equals u times sigma times v transpose. U is n by n orthogonal. Sigma is the diagonal matrix of singular values sorted from largest to smallest, and v is 9 by 9 orthogonal. The solution f is the last column of v, the one corresponding to the smallest singular value sigma 9. This is the vector that A squashes the most, meaning it maps closest to 0. That's exactly what we want. With noise-free data, sigma 9 would be exactly 0 and we'd have a perfect solution. With noisy data, it's small but not non-zero, and the last column of V is still our best estimate. We reshape this 9-element vector back into a 3x3 matrix. That's our initial estimate of F. The F we just got from SVD will generally have rank 3, but the true fundamental matrix must have rank 2. Geometrically, all epipolar lines in an image must pass through a single point, the epipole, and that forces the determinant of the F to be 0. The fix is straightforward. We take another SVD, this time of F itself. We get 3 singular values, sigma 1, sigma 2, and sigma 3. We set the smallest one to 0 and reconstruct. This gives us the nearest rank 2 matrix to our initial estimate in the Frobenius norm sense. Now, determinant of F is exactly 0 and the epipolar geometry is valid. This is a step that makes the algorithm actually work in practice. Hartley showed in 1997 that without normalization, the 8-point algorithm gives poor results. The problem is that the raw pixel coordinates range from 0 to 1920 or more. When you multiply these together to build A, you get entries spanning many orders of magnitude. This makes the matrix ill-conditioned and SVD becomes numerically unstable. Hartley fix is elegant. Before building A, normalize points in each image independently. Translate so that the centroid is at the origin, then scale so the mean distance from the origin is root 2. Apply this separately to each image using transformation matrices T and T prime. Solve for F in the normalized space, then undo the normalization. F star equals T prime transpose times F hat times T. Hartley showed this improves accuracy by orders of magnitude. So putting it all together, there were 5 steps. Normalize your points, build the A matrix, SVD of A to get the initial F, enforce rank 2 with another SVD, and denormalize to get back to pixel coordinates. In practice, you wrap this whole pipeline inside ransack. Randomly sample 8 pairs, run these 5 steps, count how many other correspondences agree with the result, and keep the F with the most inliners. But the core is always these 5 steps. So let me show you the results. First, on synthetic data where I know the ground truth. On the left, I have 10 synthetic point correspondences generated from 2 simulated cameras. On the right, I computed F using our 8-point implementation and drew epipolar lines. Every colored dot sits on its matching colored line. The mean epipolar error, that's X transpose Fx, which should be 0, is 0.034 pixels. Near perfect. Geometric consistency, which confirms the math works. Now on real images. These are from Middlebury stereo datasets, tube views of a bowling pin scene. I used SIFT to find matches, then ran the 8-point algorithm through OpenCV. Again, the colored dots in image 2 sit right on their matching epipolar lines. Notice the lines are nearly horizontal. That's because this is a stereo pair with a mostly horizontal camera shift, which is exactly what you'd expect. This confirms the algorithm works on real-world images with real feature matches. To wrap up, F maps points to epipolar lines. The epipolar constraint is linear in F entries. 8 correspondences gives us linear system we solve with SVD. We enforce rank 2 by zeroing the smallest singular value, and Hartley normalization is critical for numerical stability. Limitations worth noting are this algorithm is sensitive to outliers, which is why you use it with ransack in practice. It fails in degenerate cases like purely coplanar scenes or pure camera rotation. It only gives F up to a scale. Thank you.